Ohayo gozaimasu. Sadly, that's about the only Japanese I know. So apologies, I'm going to be speaking in English. My name is Bryan Boreham. I'm going to be talking about something which is very technical, very deep in the computers that we use, but very important. And the title is a pun. Obviously, always do puns in a foreign language. But really, what I'm going to be talking about NUMA, which means or stands for non-uniform memory access. And we'll get all into the detail of that. I'm not going to be talking about hyperthreading, which is on the abstract. I cut that in the interest of time. There's so much to talk about here. I work for Grafana. Who's heard of Grafana? Yeah, a couple of people. So most people know the visuals, the dashboard. We have this enormous cloud service where we run thousands and thousands of computers processing metrics and logs and things like that. And I work on the back end of that. I wanted to have a sign. Some people use this kind of thing, like this is where you have to pay attention. And apparently this is the official Japanese version of that sign. I thought maybe this one's better, or this one. But I settled on this one. So this is the sign for the things you should remember. This is a very detailed talk. So if you see this sign, remember. The slides are on Shed. You can download them. There's lots of links and things. OK, let's get going. So we start with a dashboard. This is one that I look at a lot. This is monitoring CPU usage of metrics ingest. We're receiving metrics into our cloud. And it's very, very steady. People send the same metrics over and over again. So one day, it looked like that. Out of these hundreds of machines, 3 of them are using way more CPU than the rest. And way more, the yellow line is the request. So 3 machines were doing something different. Now, I spend a lot of time on performance analysis, and this mystified me a lot. And, but, oh yeah, I have these slides to remind me what I'm supposed to be talking about. I changed the view to make it obvious what's going on. This took days to figure out, but so I've changed to join in the type of machine. So all the blue ones are good, and there's a lot of different kinds of machine. These are AWS nodes. All the red ones are M5A 12x large. So why is that interesting? Well, so if we learned about how computers work, we get some kind of picture like this. We have multiple CPUs in the machine. We have memory, and we have a bus. And they all talk together on the bus. Well, this is a picture of a real computer. Where's the bus going to go? You know, so the yellow things are the CPUs, and the black things are the memory. And if you connected all of those things with one bus, it would be incredibly slow. The electrical signals going all the way around the computer So this is not the way computers work. This is how computers work. Each CPU is connected to its own memory. I mean, you can kind of see that, right? The CPU is right next to the memory. Each CPU is next to the memory. And then the CPUs are also connected to each other. And yeah, there is a memory bus. There's memory bus here, 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 here. There's lots of buses. But there is not one memory bus, and it is non-uniform. So if you are here in the green, and you want to talk to memory here, it's very fast. If you are here, and you want to talk here, it's very slow. So that's what NUMA means. Non-uniform memory access. And all computers, all big ones, servers, not your desktop, maybe, we'll get to that. But big servers are all built like this. And that's what I want you to know. This is a picture of the timings. And I simplified. So basically, there's the green bit. This is in nanoseconds. So the green bit, you can talk to memory at about 50 nanoseconds. And the red bit, you can talk, it's like 140, something like that, nanoseconds. So it's like 3 times as slow to go from the fast section to the slow section. There's a white line down the middle. That's where the one core is talking to itself. So that takes like no time at all. But the green is core. This is the numbers are the core numbers. So this is 32 cores in one zone. And talking to the next 32 cores, everything slows down. So this is a Xeon. I'm going to talk about lots of different processors. I want to make a note, not everyone runs the same kind of programs I do. If you run a small program, you won't see this problem. You won't suffer from NUMA, because everything will be contained on one zone. So if you use just one CPU, or you just use like a few megabytes of memory, you're not going to see this problem. You get this problem on big programs. I work on big programs. I work on Go programs. I'm a Prometheus maintainer, for instance. And so that runs in several gigabytes of memory, and it uses lots of cores. So big programs suffer from this NUMA problem. OK, how would you know? How did we figure this out? So there are Prometheus metrics. These come from Node Exporter. There's that sign. So these metrics, you can compare memory in other zones against the local zone. This is pretty good. I mean, it gives certainly if that ratio is higher than 0, then you have a NUMA problem. But this is just memory allocation. It's not brilliant. But this is the easiest thing to do. You just Node Exporter. Most people have Node Exporter. You turn on the zone info. It's an option. It's off by default, and you get these metrics. So that's easy. You may be able to get much better data from the hardware. The trouble is, in the cloud, most of these hardware metrics are hidden by the hypervisor in the cloud. So I don't want to dwell on this. There's Intel have a page. It's getting better. Newer instances like generation 7, generation 8 are better at giving you these metrics. So if you download the slides, all the links are at the end. So just to mention that. OK, so even if you don't have any metrics, how do you look this up? How do you know how much NUMA or what kind of NUMA you have on your server? So the cloud is going to publish that, right? No. So this is what Amazon published. Google is the same. Microsoft is the same. They publish the number of cores, the amount of memory, the kind of disk, the kind of network. They do not publish the NUMA characteristics of their computers. I don't know why, but it's a fact. OK, if you log into the machine in privileged mode and run this command, lscpu, it prints out more than this when you run it. But this is what you want to look for. NUMA, they use the word node. Node is too confusing. I'm going to say zone most of the time, because otherwise the word node is showing up in too many places. Anyway, so this is the actual machine that we had the incident with at the beginning. It's an AMD, the first version of the AMD EPYC architecture, and it is hyper-threaded. So 0 to 7 are the first set of cores. 24 to 31 are the same cores, hyper-threaded. So they double up. And there are 3 NUMA zones here. So that's a good way to know what your computer is like. Bigger computers are going to have more NUMA zones. Here's one. So this is a pretty new AWS ARM, a Graviton node. This one has 64 cores in 1 NUMA zone. So you do not have a problem if you're on this machine. So I'm not trying to sell you ARM versus AMD. To some extent, if you've got a bigger ARM machine, it's going to have NUMA zones. But newer machines tend to have bigger NUMA zones. So this one is 64. This one is basically 8. Oh, and the ARM machines don't do hyper-threading. So you just get like 64. They don't double up. OK. How are we doing? Good. So there's a picture of the chip. This is the one we had the incident with. And what's interesting, inside, it's actually made up out of little chips, chiplets. So this is what leads those chips to have a particularly big NUMA problem. That each one of those things has 8 cores on it. So that's physically what it looks like. And basically everything, all chips are going to go this way. This is what they're doing to get more power out of chips. So so this is kind of the hardware explanation, or the extremely low-level view. Each one of these things has a memory controller on it. So this is one of those timing diagrams where we take every single core and time how long it takes to talk to another core. So 24 cores on the top, 24 cores on the side. And it's 32 nanoseconds at the fastest and 220 at the slowest. So there's huge difference going from a fast case to a slow case. So this is what we think was happening, that we had some of our program on one CPU, some of our program on another CPU, memory all over the place, and it's getting hit by those slow accesses. So what did we do? We stopped using M5A 12x large nodes. Well, we stopped using 12x large and 16x large, because those are the big nodes. We don't actually need such big nodes. it's kind of a dumb answer, I guess, but it took us a long time. So this is what I'm doing here, trying to get you an understanding of the basic information. To illustrate, how you could get here kind of slowly, right? You start with a small box and you run some pods on it. You're growing your business. You get a bigger machine. You run some more stuff on that. You get a bigger machine. But what you don't realize is you got the bigger machine. It's split, and your program starts suffering when this happens. So what you might want to do is use smaller machines, right? This is if each machine is smaller than a NUMA node, a NUMA zone, you will not have this problem. You will have to pay again if you have another machine. It has another kubelet, another kernel, and so on. So you don't have to pay those costs twice. But I would be very cautious of being in that situation. And another way to look at it is you could use VMs that are like that size, right? When you rent a computer from Amazon or Google or somebody, they can carve up the big machines into smaller machines. So if you rent a VM that's that size, it's not going to have this problem. What does Kubernetes give you? I'm at a cloud native conference. I should talk about Kubernetes. So inside kubelet is a thing called the CPU manager. You can turn on the CPU manager policy. So by default, it does nothing. It just kind of spreads your stuff wherever it goes. If you turn on static, then guaranteed pods, so that's where the request equals the limit. With integer request, so like you request 10 CPUs or 6 CPUs or 1 or whatever, not 5.5. Then it will align your CPU allocations at the NUMA boundary. So this is what Kubernetes will do for you, but only if you turn it on. So turn on the CPU manager. You may not want to use guaranteed pods, but that's the only way to get this advantage. The sign. There's another thing called the topology manager. So if you Google for this, if you Google Kubernetes and NUMA, you might find this. This is to locate a set of containers or even a set of pods on the same NUMA zone. And nobody does that, right? That's a very, very niche problem. My problem is I have one program and it's running on multiple nodes. So you don't really need this. Don't worry about this. So do this. There's also that. If you're the 0.01% of people who need this, then that's fine. Okay, one more thing. Uncore. Who's heard this word? No, me neither. So it turns out this is the word. Well, okay, let me explain this picture. It's a nice picture I drew in Grafana. This is plotting. We have a lot of pods that are doing the same work, right? They're very, very well load balanced. For the same work, the pod CPU utilization can go from about 36 to 80 of what we request, the percentage of request. And if you plot that against how busy the node is, you get a nice diagonal line, right? So this is pod CPU against node CPU. And the load balancing is very, very good. There's nothing stupid going on here. This is uncore. So what does that mean? So if those are cores in your CPU, And the level 1 cache, the level 2 cache, those are all attached to the core. Then uncore is everything that's not in the core. And this is a word that Intel and AMD and so on they use. I didn't make up this word. Particularly things like the L3 cache, which they call the LLC, the last level cache. The memory controller, the TLB. There's a bunch of things outside of the cores. These are shared resources. And so as you load up the node more, these shared resources get overused. They become the bottleneck. Right. So I think that's what's happening here. So basically, don't load up your nodes too much. This is pretty good, actually. We only, when I drew this picture, we were up to about 75%. I mean, it's an economical question. If you can load your nodes up, you don't pay so much for nodes, but your programs will slow down. So yeah, so that's another word, uncore. As you load up the machine more and more and more, the same program will slow down. So there's another thing in Kubernetes, CPU manager. This is new in 1.32, so very new. And you can align the CPUs by uncore cache. So when you maybe wait a few versions and then try this out. So that's cool. OK, that's pretty much what I prepared. I wanted to explain this thing that is going on inside your computers, which is NUMA, non-uniform memory access. Stay within those NUMA zones. So either don't use big machines or use VMs that carve up the big machines, or just run small programs if you can. Everything is non-uniform. Not just the memory, the caches, the core itself. If you have hyperthreading, we talk about noisy neighbor programs where you're running next to a very busy, expensive program, or sometimes the noisy neighbor is you, and that's what happened to us in the incident. Okay, so I have a few minutes for questions if anyone has some. Does anyone have a question? A hand over here, thank you.
Thank you for the presentation. In the slide you mentioned that you have some real-world impact that you can ensure to AWS and Google Cloud. Could you show some example of the real impact of this NUMA application?
So the question is, can I share some real-world impact of this? Well, I don't know if I can get this slide. Can I get it all the way back to? Yeah. So I mean, this was the impact that the processes were normally using about 8 CPUs, and then they started using 14, 15 CPUs for the same program, for the same workload. So in this one case, that was the impact. It was like double. I've spoken with people. Milin Chabi, I put on the thank you slide at Uber. He reckoned there's about a 15% impact across the whole of Uber. So, I mean, it depends what you're doing. Like I say, if you run small programs, you won't suffer at all. Linux will do the right thing. We'll put the memory with the CPU. But yeah, so there's a range what the impact can be. Somewhere between like 10% and 2 times. Was there, I think there was another question here.
Thank you for exciting talk. My question is about not NUMA, but similar problem like cache related problem. Some workloads suffers from the related to the cache performance issue. So, is there any approach to detect or get the metrics about cache related performance issues or not?
Okay, so question is, can we get metrics about cache performance or cache hit rates, cache miss rates? And I guess you mean CPU cache, right? Yeah. So so that's this guy, yeah. So not those ones, but in perf. Perf is the tool that will give you those on Linux, that will give you those very low-level hardware metrics, hardware counters. And so again, check this list. It tells you which machine, because some virtual machines, the VM, the hypervisor will hide that information. But if you run on a metal instance or some of the newer, bigger machines, will expose those counters, and you get metrics for the L1 miss rate, the L2 miss rate, the L3, the LLC cache miss rate. Yeah, you get all of that detail. So the tool to look at is perf, and then you have to find a machine that gives you the numbers. Because if you run on just a VM like WSL or something, like just says, nope, never heard of that. So yeah, look at perf and look at those L1, L2, LLC counters.
Thank you.
We got a question here.
Hi, I wanted to ask if at Grafana there's, like, if you guys have a plan to essentially work around this issue moving forward other than just using smaller machines, like, are you going to the software developers and saying, hey, can you break up your application, or is there something else? Right,
okay. So the question are what else are we at Grafana doing? So we write pretty much all the backend in Go, and Go is currently oblivious to NUMA and things like that. So they actually, in the next version, Go, whatever it is, 125 that's coming out in a month, that will actually respect your Kubernetes CPU limit. I won't go into all the details, but it gets a little bit better. But yeah, so setting Go max procs is something we do. Try and set that fairly close, and that really helps when you're using Go, which we do. Yeah, be very careful with your choice of VM, your instance on Amazon or Google or Azure, whatever you're using. That is something, we were basically blindsided by this because we weren't thinking about it, and then we learned about it. So nowadays we're very careful about which kind of nodes we use, and we just don't use those like 192 core nodes or whatever, because we're going to hit this problem. In terms of writing the software different, yeah, I mean, kind of the same thing as horizontal scaling. You know, if you have a program that needs 24 cores or something like that, you probably didn't horizontally scale it. If you did horizontally scale it, you can kind of pick, you know, am I running on like 1 core times 1,000 or 10 cores times 100? And yeah, there is a bit of a sweet spot there, you know, and we do some experimentation to try and figure out where we are. So yeah, I mean, we're still on a voyage of discovery. I would love to get better data. It's actually this page. It's currently very hard to get this data. So as a metrics and monitoring company, I would love that we could just provide this. But today it's too hard.
Okay, thank you.
So that's probably a good note to close on. Thank you all for coming.